Hello, my name is Mike, and in this presentation I will explain a machine learning model for diabetes prediction. The goal of this project is to predict whether a patient is likely to have diabetes based on medical diagnostic measurements. This is a binary classification problem because the model predicts one of two outcomes: 0, meaning no diabetes, or 1, meaning diabetes. This kind of model is useful as an educational example of how machine learning can find patterns in health-related data, although it should not be treated as a replacement for medical diagnoses. For this project, I used the Pima Indians diabetes dataset. The dataset contains 768 patient records and 9 columns. There are 8 input features and 1 target column called outcome. The input features are pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes, pedigree function, and age. Some of the most important medical indicators are likely to be glucose level, BMI, insulin, age, and family history related risk, which is represented by the diabetes pedigree function. The target variable is outcome, where 0 means the patient tested negative for diabetes and 1 means the patient tested positive. Now I will briefly explain the code. First, I import the libraries. I use pandas and NumPy for data handling, scikit-learn for splitting the data set, scaling the features, and evaluating the model, and TensorFlow Keras to build the neural network. Next, I upload the data set in Google Colab. I use the Colab file upload tool to upload diabetes.csv, and then I upload it with PD read CSV diabetes CSV. I print the first 5 rows, the data set information, and the class balance so I can understand the structure of the data before building the model. The class balance shows there are 500 patients 500 patients in class 0, meaning no diabetes, and 268 patients in class 1, meaning diabetes. This tells us that the data set is not perfectly balanced because there are more non-diabetic cases than diabetic cases. For pre-processing, I first check the missing values. One important issue with this data set is that some medical measurement contain zeros that are not realistic. For example, a glucose level, blood pressure, insulin value, skin thickness, or BMI of 0 is likely representing missing data rather than a true medical measurement. Because of that, I replace zeros with these columns. Down here, with NAN. Then fill them using the median value of each column. I do not replace zeros with pregnancies or outcome because those columns can correctly contain 0. After cleaning, I separate the features and the target. Then the feature matrix X contains all columns except outcome, and Y contains only the outcome column. Then I use standard scalar to scale the feature value. Scaling is important for neural networks because the model trains more effectively when the input features are on a similar numerical scale. Then I split the data into training and testing sets using an 80-20 split. This gave me 614 training samples and 154 testing samples. I also use stratification, which helps keep the same proportion of diabetic and non-diabetic cases in both the training and testing data. For the model, I use a small feed-forward neural network. The first hidden layer has 16 neurons with RELU activation. The second hidden layer has 8 neurons with RELU activation, and the output layer has 1 neuron with sigmoid activation. I use sigmoid because this is a binary classification problem, and sigmoid outputs a probability between 0 and 1. The model is compiled using the Atom optimizer and binary cross entropy loss. Atom is a common optimizer because it usually trains efficiently without requiring too much manual tuning. Binary cross entropy is appropriate because the target has 2 classes. The model is then trained for 100 epochs with the batch size of 16. I also use a validation split during the training, so part of the training data can be used to monitor performance while the model learns. After training, I evaluate the model on the test set. My final test accuracy was about 72.1%, or 72. This means the model correctly classified about 72% of the unseen test examples. However, accuracy alone is not enough, especially in health-related classification problems. That is why I also look at precision, recall, F1 score, and the confusion matrix. For class 1, which represents diabetes, my precision was 0.61. Precision answers the question when the model predicts diabetes. How often is it correct? My recall class for 1 was 0.56. Recall answers the question out of all patients who actually has diabetes, how many did the model correctly identify? My F1 score for class 1 was 0.58. The F1 score balances precision and recall, so it is useful when we care about both false positives and false negatives. The confusion matrix was 81, 19, 24, 30. This means the model correctly predicted 81 non-diabetic cases and 30 diabetic cases. It incorrectly predicted 19 non-diabetic patients as diabetic, and it missed 24 diabetic patients. Overall, these results show the neural network learned useful patterns from the dataset. But it is not perfect. The model performed better at identifying non-diabetic patients than diabetic patients. The recall for the diabetes class was 0.56. Meaning it caught about 56% of the actual diabetes cases. In a real medical setting, this would need improvement because false negatives are important. A false negative means a patient who actually has diabetes is predicted as not having diabetes. However, for a small neural network on a small data set, the result is reasonable and demonstrates the main machine learning workflow. In conclusion, this project demonstrates the process of loading a data set, pre-processing the data set, splitting it into training and testing sets, building a neural network, training the model, and evaluating its performance using accuracy, precision, recall, F1, and score, and confusion matrix.